Hi there, Mike here, getting over a cold, and we're eating pretzels in the background, so it might be a little crunchy. They're good. We want to talk about the central limit theorem, and we'll have two videos on it. This is one of them. There's another video which has more of the symbols and the math involved. Central limit theorem is a big idea, it can be confusing to people. The word central means mean, middle of a distribution. It's a central limit theorem because it's what happens to the mean. That's why it's called the central limit theorem. And what we see here, and you can go to this website on top. No, I don't want to do that. Touch screens are bad. You can go to this website here and check it out more and play with it yourself. The top thing here is the population. Quite boring to work with a population like that. Let's work with something that doesn't look normal. We're going to mess it up a bit. Take my finger and just... We don't want anything that's normal looking. We just want something... Okay, what we're going to do is generate data from it. We're going to take samples of size 5. So we generate data from the population, and that blue thing is X bar. Samples of size 5, if I click on the right thing. And that happens to be X bar. We'll do it again, and that happens to be X bar. Now, this is the idea of sampling distribution. If we take samples of 5, form X bar, and do that many times, this is a thought experiment. You will not do this in practice. In practice, you'll take one sample because of money and time and all kinds of other things. But if you take many, many samples of size 5, you form X bar each time, what would a histogram of the X bars look like? And that's what the third panel is down here. Let's do 10,000. And what does that look like? It looks bell-shaped. We started with something that was not bell-shaped, and we have something that looks bell-shaped. Now let's try what happens if we increase sample size. Let's go up to 20. Oh, this is going to be a lot of fun. Samples of size 20 form X bar. Boom. Samples, I don't know why I'm doing this. This is stupid. Samples of size 20 form X bar. Do it 10,000 times. A pretty nice bell-shaped curve. That's the central limit theorem. It says no matter what you start with, a histogram of X bar, not your data, X bar of your data, the average of your data, follows a bell-shaped curve. Now, if you start with something normal, let's clear the bottom. If you start with something normal, that's uniform, that's normal. You start with something normal, insanely boring. It works for any sample size. Sums of normals are normal, so it doesn't matter. If you start with something normal, you always get something normal. What's cool about the central limit theorem, though, is you start with something that's not normal. And you take repeated samples, you should get something that's normal. Oh, you don't here. Sample size actually matters. The central limit theorem says that no matter what you start with, eventually the histogram of X bar will be normal for some n. Doesn't tell you what n is. We generally say for n bigger than 30 in this class. So for some really, really weird data sets, it might be a lot bigger than 30. But here we only did n equals 2. Let's try n equals 20, 25. Pump up the volume. Boom. It looks normal. It could be a discrete data set. I don't know if I can draw a discrete data set. It could be really, really a little up over here. Let's try to get rid of all the stuff down over here. Get rid of that. A really, really weird data set. Let's do animated. Well, let's clear. Sorry, let's clear lower 3. Let's do an animated. One more animated because I'm an idiot. And we're grabbing 25 and we're going to farm X bar. So this third one is X bar. It takes a long time to grab 25 bits of data. Let's do 10,000 of these and look at that. You start with something very weird looking, kind of like a bathtub, we call that. Excuse me. And we look at X bar follows a bell-shaped curve. Why do we care about this? Well, the fact that X bar follows a bell-shaped curve, we know a lot about bell-shaped curves. We know where most of the area is. We know it's unlikely to be in tails. We have a really good idea about X bar. So it's very powerful. It says you don't have to know what the underlying population is. If you're happy to just work with X bar, you know X bar is going to be normally distributed, as long as n's big enough, and that's generally around 30. That's the CLT in a nutshell, seeing it visually. Look for the next video to see some of the math behind the CLT. As always, hope you're having a great night, and we hope to talk to you soon.